Good afternoon. My name is Peter Shields and I'm pleased to welcome you all to today's webinar, Criteria for Lower Cost Air Quality Monitoring Systems, How Near is Near Reference? This afternoon, we're fortunate to have Dr Geoff Henshaw, the Chief Technology Officer and co-founder of Aeroqual in New Zealand, to present on this topic. Geoff has vast experience in this area and I'm sure you'll find him interesting and informative. I'll now hand over to Dr Geoff Henshaw, who's kindly agreed to present today from New Zealand. So thanks, Geoff. Over to you.
Okay, thank you, Peter. As Peter said, I'm talking about low-cost air quality monitoring systems today, and really looking to understand how good are they getting. Some of the drivers for looking at new sensing technologies are listed here. First of all, there's an increasing awareness of the spatial variability in air pollutant concentrations. So as land use gets more complicated, as emitters get closer to receivers, then there's going to be more awareness of the concentration gradients across from emitters affecting local populations. And people are more interested in understanding how these concentration gradients vary across landscapes through urban areas or rural areas. The second driver is cost. So reference networks using reference equipment can be expensive, and this limits the number of these kinds of sites that can be deployed. Lower cost technologies offer the ability for more sites to be monitored and therefore enabling you to identify spatial variability between different sites. The third driver is the democratisation of data. The idea that citizens want access to localised information in real time. And I think this is becoming we see this becoming increasingly important in countries which perhaps don't have an existing network and they really want to, and there's a growing growing number of informed citizens who want to have information about the air that they breathe. And this is about enabling them to change their behaviour according to the air quality that they find themselves breathing. Fourth area is technology improvements. There's certainly been a large number of new devices and new technologies become available that are enablers for being able to measure the gas pollutants at lower levels. And so we have sensors which can measure ppb levels. And these are the levels at which we start to see health effects. And the last area is that people are becoming just more aware of how air pollution affects their health, and increasingly there's medical evidence that health effects are evident at lower pollution levels. And that means that the spatial variability becomes increasingly important. And so all these five drivers are driving towards looking at different types of technology and also different types of deployment of technology. There are a number of devices which gas sensors on the market, a wide range, and these extend from fully weatherproofed. They come with their own communication systems, and they can be mounted to a pole. The idea is that this sort of technology is very easy to deploy, but probably slightly higher cost. Or you can get other devices which are a single piece of electronics or even a single sensor, and these are devices which are much lower cost but would require some level of integration before you could deploy them. So there's a wide variety of technologies also, electrochemical sensors for measuring different gases, photoionization detectors for VOCs, heat of metal oxide sensors for ozone and NO2, and NDIR sensors down here for measuring CO2. So different technologies for different kinds of gas measurement. For measuring dust, again, there's a wide variety of devices, more or less a single technology actually. They're mostly light-based, using a laser diode and a detector, looking at measuring light scattering. And these again can be found from a single sensor board, which are for tens of dollars each, through to a complete instrument, including inlet and pump, and data acquisition system, which are on the order of $1,000 or more, $1,000 to $10,000. So again, a wide range of instrument types, but also These are cheaper than the existing reference technology, which allows you to deploy more of them. A big question people have is how to evaluate these kinds of new technologies. There are a number of studies around the world that are either have been completed or are ongoing. And for example, the US EPA have a sensor performance evaluation program looking at ozone and NO2 in the lab laboratory studies. That's available through their US EPA website. The European Union had a project called MAPPOL, which was looking to validate low-cost sensors and to determine whether they would be suitable for regulatory monitoring. And I'll talk a little bit more about that shortly. NILU, the Norwegian Research Institute, they've had a laboratory study underway and have evaluated a number of sensors and devices that are commercially available. And lastly, there's a field study going on in LA run by the South Coast Air Monitoring Department called AQSpec, and they are evaluating sensors, both gas and dust sensors, in field studies as well as laboratory studies. So I would certainly encourage you all to go and look for these studies, and they give you a good understanding of the performance of these lower cost devices. US EPA have been active in this area for a number of years now. Firstly, they've created a roadmap for next generation air monitoring, where they have laid out the types of applications and uses for this for lower cost technology. And there's some really good reading in that. Also, it discusses the drivers behind the need for this kind of monitoring technology. And they've also issued an air sensor guidebook, which is a guidebook for how to use these lower cost devices. And that's quite useful if you're new to measuring air quality or if you are unfamiliar with these kinds of sensors. So I would certainly encourage you to access those documents, and you can see that you can get that information via the web link at the bottom there. How good should the new technologies be? And here's a slide that's taken from the US EPA document, where they have estimated the precision and bias error for different types of monitoring applications. The regulatory monitoring, and the US EPA talks about a tiered system. So Tier 5 is our familiar regulatory monitoring network, which have low values for the precision and bias error. And then as they've identified other types of application area, those errors are allowed to increase. And the idea being that these kinds of lower cost technology can be used, even though they have higher uncertainty, they can be used for certain types of applications. So this is really starting to map what kinds of applications are suitable for. The European community has acted a little bit more differently. They have identified data quality objectives for their fixed network. So they set uncertainty levels for their reference network stated here. So 15% for SO2, NO2, carbon monoxide, and 15% for ozone and NO2. 25% for PM. But interestingly, they've also set guidelines for data quality, uncertainty, maximum uncertainty levels for indicative measurements as well. And as we'll see, with these in place, it offers an opportunity to see whether any of the emerging technology can reach these kinds of uncertainty budgets. And so that's something that the European Union has been studying for a number of years now. Within the EU, they have what's called equivalence certification. So if a new technology can demonstrate equivalence to reference methods, then they are permitted to be used in the European Union networks. The demonstration of equivalence requires both laboratory and field tests. The field test is usually a 3-month co-location and a calculation of the expanded relative uncertainty. No standard exists or a test method exists for indicative gas monitors, but a working group has been established to look at this. However, there is an indicative standard for PM10 and PM2.5, and this is run through the UK agencies, Environment Agency's certification program called MCerts, and several dust monitors have passed this test, which involves both lab and field tests. So there is an intention to try to develop test methods for these types of lower cost sensors. And as I described earlier, the MACPOL project from the European Union attempted to lay out a test protocol for these kinds of sensors. It consisted largely of a laboratory part, a number of steps involving looking at identifying the sensitivity, response time, short-term and long-term drift, interference testing, etc. And if the expanded relative uncertainty was low enough, they then suggested that these sensors could be put outside into field test and field tested, and that would be a way of determining whether a sensor is accepted as an indicative method in the under the regulatory framework from the European Directive. One of the challenges with that kind of protocol is that you need a test rig that looks like this, and it's a very complex piece of test equipment, and it's required because the test protocol that was described involved measurement of influences of humidity and temperature and pressure, etc. And to really understand all the effects of those parameters on sensors means that you need a very sophisticated test rig. Now, this is challenging to replicate in other laboratories, so it's not something that is easily accessible by those who are interested in understanding sensor performance. And in fact, one of the results from this European Union project was that even though the sensors that had passed some of the testing under this laboratory protocol, when placed out in the field, did not reproduce or did not show the same sorts of behaviours. So there is this discrepancy between the laboratory and field tests for these kind of sensor technologies. So it seems to me that it's important that the field test component of the assessment is really emphasised, since it's quite difficult to develop a laboratory protocol that suits all these kinds of sensor technologies. So that's where we will go to next. But before we get there, I think it's important for you to understand that behind the sensors there will be a scientific basis for the measurement, and it's important that there is some understanding of what's going on behind the measurement in order for you to more completely understand what are the potential impacts in the field and during use that might affect that measurement. So it's always, this slide is, I'm not going to go into detail on it, but it's a reminder for me to tell you that whenever you're considering looking at lower cost sensor technologies, that you do have an understanding of the underlying science behind it, so that you can start to evaluate where it might be viable. The European Union equivalence field test is defined in the test method, and there's also a calculation tool here which allows you to take co-located data, drop it into the spreadsheet from this link, and it will spit out a pass-fail criteria, which is very useful and a simple tool that can be used to assess co-located data. So the field test program is to take the instruments, take the sensor instruments, co-locate them with a reference station, and then to collect hourly data, typically hourly data, but for dust it would be daily average data, and put the data into the spreadsheet, and it calculates the standard relative uncertainty according to a particular limit value. So you can enter in a particular limit value for the criteria pollutant you're looking for. So for ozone, for example, you might put in 100 ppb as the limit value, but you have the choice of selecting that. So I just want to run through an example of an equivalence test for one instrument. It's our Aeroqual AQM65. This instrument measured ozone, NO2, carbon monoxide, NOx and PM2.5. It was a 3-month co-location study at Auckland Council site. We were lucky enough or thankful that they were able to share the reference site data for us. This is just an example of a graph of the hourly data. The red line is the ozone from the reference station, and the black line is the Aeroqual ozone module in the AQM65, and that's 3 months worth of data. There were no calibrations of the ozone, of the Aeroqual ozone. We just wanted to let it run. Here is the drift over that time. So this is the hourly ozone 1 hour average difference between the AQM65 and the reference station, and this is ppb levels here over a 3-month period, and you can see that the drift, there was no noticeable drift, but there was variances of a few ppb. So the instrument is very stable. Equally, this is the NOx data over that 3-month period, and again a very good correlation with the reference site data. So if we throw the ozone data, hourly average data, into the spreadsheet, this is the output, an example of the output, and you get a standard relative uncertainty measurement, percentage measurement according to a particular limit value, and the criteria for equivalence is that that needs to be less than 15%. And so you can see that this sensor technology is certainly in some instances able to meet this equivalence criteria. If we do that for NO2, again, the scatter is a little bit higher, but we're still within the 15% criteria for equivalence. If we look at PM2.5, in this case the expanded relative uncertainty is 42.3%, considerably higher. This is not within the criteria for equivalence, 25%, but it is in the within the criteria for an indicative measurement, which is data quality, expanded relative uncertainty of 50%. So this technique is taking the field test data and using orthogonal regression and analysis to determine an expanded relative uncertainty. Does give you a method by which you can determine if new sensor technology is able to meet the requirements that you wish to use it for, whether it's you need data that is at a reference level or whether you need data at an indicative level. Here's another example. This is a handheld instrument that Aeroqual manufactures called an S500. This was a study done a number of years ago now by a group based in Houston, Texas, who were interested in measuring the spatial variability of ozone through the Houston area. They did a co-location study where they mounted the S500 in an upside-down weatherproof enclosure and mounted that beside one of the reference sites within Houston, and ran that for a couple of months. And this is a slide of the data set. Red is the reference data and blue is the Aeroqual 500 data. And if we take that and throw that into the spreadsheet, then to determine equivalence, we can see that even that handheld instrument met for equivalence with a limit value of 75 ppb, which is the hourly average, the 8-hour average for ozone in the US. Just in summary here, here's an example of the limit values that we used to do the calculations and the calculation of the relative uncertainty for the measurements. And you can see that for the majority of the gas measurements, they were within the EU Directive for equivalence to the reference method, and the PM2.5 was able to meet the indicative standard of being less than 50%. So you can see that the technology, the new sensing technology is improving significantly, and by using a field test, the field test protocol has been defined for equivalent to framework. That is a good method for evaluating whether or not the data quality that you're looking to achieve with a sensor can be achieved. Finally, if you plot the calculated expanded relative uncertainty as a function of the limit value, this is a calculation looking at ozone from both the S500 and the AQM60, then you can see that as the limit value drops, the expanded relative uncertainty calculation changes, and this gives you a way of determining whether or not, based on the field data, whether or not the technology will provide you with sufficient data quality for a particular application. So if you're looking at very low levels of ozone, then you really need to be using a more sophisticated instrument than simply a handheld if you wanted to achieve a low uncertainty budget. So that's another way of thinking about the spreadsheet and how you might apply it to particular technology and application. So final conclusions. Recent field tests show that some of the new generation air monitoring instruments are approaching the data quality performance of reference instruments. Certainly that's true for gas instruments, but the PM10 and PM2.5 measurements are still at largely an indicative level for the lower cost devices. And this is function, I think, of the light scattering technology and the inherent uncertainties and errors that creep in with that sort of technology. Secondly, the European Union Field Test Protocol, I think, provides a useful methodology for evaluating these new instruments. And by doing the testing outdoors under field conditions, you have a better understanding of whether they're going to be useful for the types of applications that you might be using them for, rather than relying on a laboratory test. And thirdly, calibration and traceability of new instruments remains an important and challenging for large-scale networks. So the idea behind putting a lot of these sensors out into a network across an area and then maintaining that network is still a challenging idea. The sensors becomes difficult to if there are lots of sensors, it becomes challenging to be able to maintain the calibration throughout the network. But there's a great deal of work being underway looking at the way in which networks of sensors can be validated through a network approach. So instead of calibrating and individually calibrating each instrument or sensor, you would look at the network as a whole and develop tools to enable you to assess the validity of data coming from a particular instrument, and then potentially recalibrate that based on next nearest neighbours. So the sort of ideas are being worked on at the moment, and I think will be a great importance if these large-scale sensor networks are going to be viable. Okay, so thank you for your attention. I hope that was useful.
Just like to say thank you all for attending today. I trust you found it useful and interesting. Airmet represents the Aeroqual product range in Australia, so if you'd like any further information on these products, please feel free to contact us. And finally, thank you, Geoff, for your time today. Very informative and interesting presentation. Thanks very much.
You're welcome. Thank you.